let's see what happens when we divide our radical expressions. In this first expression, we have the square root of x cubed all over x. This here means division, but if you'll remember your properties of exponents, you'll recall that x cubed over x can be reduced to, remember the exponent 1 here on the x? I'm going to subtract 3 minus 1 to get x squared here. So again, we're incorporating our rules of exponents in this first example. Now that we reduced to the square root of x squared, you're a pro at this now. I know you know that the square root of x squared reduces down to x. Let's take our second example. In our second example here, we had the square root of 49 all over x squared. Now, if we look at each of these individually, you recognize, I'm sure, that they're both perfect squares. So what we can do here in the division of radicals is to split this into the square root of 49 over the square root of x squared. Once we do that, we can then simplify the square root of 49 into 7 over, and as we just saw, the square root of x squared is simply x. So we can simplify this expression, the square root of 49 over x squared, down to 7 over x. Let's look at some other problems involving division of radicals. Now, in this next problem, we're going to have to recall some definitions that we learned a long time ago. Let's look at this expression, 9 over the square root of 7. Now, our job is going to be to simplify this expression. You might ask yourself, it looks simplified to me. 7 is not a perfect square. I cannot simplify that. You're absolutely correct, but there's one little catch. Radicals are in simplified form when the denominator does not contain a radical. Notice this fraction, denominator, we have the square root of 7. This expression is not considered simplified when it has the radical in the denominator. So our job is going to be to get rid of the square root of 7, or what we call it in fancy terms is rationalizing the denominator. Now again, I just said we'll have to remember some of our old terminology. Remember, a rational number is not a square root. We want to rationalize, which means we want to write it as a number that can be expressed as a fraction, such as the numbers 2, 3, 4, or 5. Right now we have the square root. How do we get rid of it? Well, remember, since we have an expression, we cannot just take that expression and multiply by any number we choose. If we do, we'll be changing the value of that number. For instance, let's say you had $100 in your checking account. If you decided to multiply by, let's say, 5, you now have $500 in your checking account. That would be good for you, but you can't just take a number and arbitrarily multiply by some other number, because you can see it changes the value. What we can do, though, is multiply by the number 1, because we know if we multiply by 1, we do not change the value of the number. Now, besides just multiplying by the number 1, we're going to multiply by a fancy form of the number 1. I'm sure you would agree that if I look at this number, 2 over 2, that's equal to 1. 5 over 5, that's also equal to 1. 100 over 100, that's also equal to 1. So if I take and multiply my number here, 9 over the square root of 7, by any one of these, I'm changing the form of the number, but not the value, because these really represent the number 1, thus not changing the value. Now let's continue on our list. What if I had happy face over happy face? Can I multiply by that? Sure I can. Anything over itself is equal to 1. So now what we're going to do is incorporate our radicals. Would you agree that the square root of 7 over the square root of 7 has that value 1. Indeed it does. So what we're going to do then is we're going to take our original expression, which is 9 over the square root of 7, and our goal, remember, is to eliminate this radical in the denominator. So we're going to multiply by a fancy form of the number 1. In this particular case, we're going to choose to multiply by the square root of 7 over itself. Remember, that's equivalent to 1, so again, we're not changing the value of our original number, we're just going to change the form. Now let's see how that helps us. In the numerator, we get 9 times the square root of 7. Now look what happens in our denominator. We get the square root of 7 times the square root of 7, which is the square root of 49, or simply 7. Now you may ask yourself, this expression that we came up with looks a bit more complex than our original expression. You're right, it looks a bit more complex, but what we wanted to do, and which we accomplished by this method, is we eliminated the radical in the denominator. This now is considered simplified form for a radical. Why, you might ask, do we do something like this? Well, if you were asked to add fractions that have radicals in the denominator, it would become much more difficult to find that common denominator. If we change the denominator, as we did in this particular problem, to a rational number, it's going to be easier for us to find that common denominator. That's why we go through this whole procedure. Now, let's go on to another expression. Let's say in this problem, we want to simplify the square root of 2x over the square root of 8x. Well, in this particular case, what do we have? Well, we have 2x and 8x, and I see a lot of common factors there, so what we can do is we can rewrite this expression under one radical sign. 2x over 8x. Once we write it that way, I think you can identify that we can divide out these x's at the same time. 2 goes into 2 once, into 8 4 times. So all we have left here is the square root of 1/4. Now I know you know that 1's a perfect square and 4 is a perfect square, so this reduces simply to the fraction 1/2. That one turned out a little bit easier probably than. Now let's try one more problem, and let's go back to that idea of not having radicals in the denominator. Let's look at the expression 4 over the square root of 3 plus the square root of 5. Now, because of not the last example, but the one right before that, you may be thinking, I think we should multiply by something like the square root of 3. Well, don't write this down, but just look and see what happens. When I do this, I'll get 4 times the square root of 3 over, and I'm going to use my distributive property, and you're right about this, the square root of 3 times the square root of 3 is 3 plus, but look what happens, we end up with the square root of 15. Now, did we eliminate all radicals? No, we didn't. So what we're going to have to do is use another procedure, and that is this. We're going to multiply by what's called the conjugate of the denominator. The conjugate of this denominator are the same two numbers with the opposite sign. So we're going to multiply here by the square root of 3 minus the square root of 5, and again, because we cannot change the value of the number, we can only multiply by the number 1, we're going to multiply by the square root of 3 minus the square root of 5 all over itself. So notice here, this just represents a fancy form of the number 1, and now watch what happens to my expression. We're going to have to incorporate a couple of different properties we've used in the past. First of all, in the numerator, we're going to have to use our distributive property. So here we get 4 root 3. Here, when we distribute, we get minus 4 times the square root of 5. So far, so good? Now, watch what happens in our denominator because we're multiplying by that conjugate. When I do FOIL, you're going to see that we don't have to O and I anymore. Here, we get the square root of 3 times the square root of 3, which is 3. Now, think with me here. I'm not going to write it out, but just think. O in FOIL yields the square root of 15 with a negative, so minus the square root of 15. I yields positive square root of 15. So negative square root of 15 plus positive square root of 15, 0. We've eliminated that radical. Now we still have to do L in FOIL. Here we have the square root of 5 times and minus the square root of 5, which gives me negative 5. So notice what we did is by multiplying by the conjugate here, we eliminated those radicals. So the rest of our job then, 4 root 3 minus 4 root 5 all over 3 minus 5, which gives me a negative 2. Now, if you're thinking that looks good, but there's something tricky going on with these 4s and 2s, you're right. What we're going to do now is factor out that 4 and write this as root 3 minus root 5 all over negative 2. Now that we did that, we've got a product we can reduce. Now what we'll do with this negative sign is we'll just bring it to the numerator. Negative 2 goes into negative 2 once. Negative 2 goes into positive 4 negative 2 times. So that tells us then that our final solution is negative 2 times the square root of 3 minus the square root of 5. And notice we achieved our goal, and that is we eliminated the entire denominator in this case, but certainly we eliminated any radicals that were in our denominator.